Now, let's look at one example of the application of center of mass. The two-body problem. Okay, that's a very important problem in astronomy and celestial mechanics. Like you want to study the motion of the Earth move around the Sun, or the motion of the Moon around the Earth. Okay, so Sun and Earth. So it's a typical problem of two-body problem. But here, so in fact, the two-body problem is solvable. Two-body problem is always solvable. You can decouple the two-body problem into two motions. Okay, one is motion of the center of mass. Okay. In this case, okay, you can probably cannot see it here. We actually have a center of mass here. Okay, this is the center of mass. Okay, the cross here. In this case, it's not moving at all. And of course, in the more general case, the center of mass will move. When the center of mass is moving, both of the objects are moving with the center of mass. Okay. So that's the motion of the center of mass. Another is a relative motion. So it's what you can see from this. In fact, this motion is relative motion. And the relative motion is that you can think about this object are moving around the center of mass. This object is also moving around the center of mass. So you can try to decouple the motion. If you don't do this decoupling, if you just look at the two objects, it's quite complicated. And this is even the most simple case. The two objects are, the mass of the two objects in this case are the same, and this one is not the same. Okay, this is more a little bit different. Okay, there is no intersection between the two objects. Okay, so that's a two-body problem. And okay, and what I would like to comment is that usually we say that the Earth is moving around the Sun. But precisely speaking, we have to select this. Both the Sun and the Earth are moving around their common center of mass. Okay. It's just because the Sun is much, much larger than the Earth, much, much heavier than the Earth. Okay. So the center of mass for the whole system is almost the center of mass for the Sun. Right? Okay. For example, this is the center of mass for the Sun without considering the Earth. Even you add the Earth, the center of mass only moves a little bit to here because it's so small, Earth compared with the Sun. So actually, they are moving around the center of mass for the two objects. But since it's, the 2 points are almost the same, so we just simply say that the Earth is moving around the Sun. Okay. So when the two masses are quite different, we can simplify the problem. Okay. So that's a two-body problem. Usually when you go further to study the classical mechanics, you are required to solve this kind of problem. Not very difficult, but you just, if it's three-dimensional, it's kind of you need to write a lot of things. Okay, now what I would like to talk about is the three-body problem. Okay, unfortunately, we can't do the simulation. We can do it next time. So the basic idea is that the two-body problem is completely solvable. Okay? In fact, it's not very difficult. All of you here can solve the two-body problem with a little bit training. Okay? And three-body problem, you just add one more. It becomes totally different. Three-body problem is very complicated. And in general, it's not solvable. You cannot even solve it. Only three bodies. You cannot solve it. It can only be solved for some special cases. For example, one mass is dominant, is huge dominant. So like so you can see this is kind of make us strange that even the three-body problem, like you have sun here, you have Earth here. If you have the moon here, if you add the moon here, if you only consider this quite similarly simple situation, this one cannot be solved exactly. You can only get approximate result. Okay. And the idea is here. Okay, we're going to do the simulation here. If you have three bodies and you try to calculate the trajectory, okay, you will see that, like for the two-body problem, you have some quite periodical trajectory like this. Okay, they will repeat it forever. But for the three-body, any trajectory becomes totally irregular. So if one object starts with here, the trajectory, if you try to do the numerical simulation, you will see that the trajectory may be like this. Okay, finally we do something like this. It's totally irregular. There is no, you cannot predict it in the long term. And probably you can say, okay, even it's irregular, can I just track it 1.15 to still get this? But this trajectory I'm plotting here is approximate. We don't really know what happens to later, because there is something called the perturbation. In the reality, we always have the perturbation. Any small change, like the air, if we consider some object moving in the air may apply some perturbation. The wind, you have the wind, even this very small wind, right? Or even you don't have the air in the vacuum, very far away you have some star to apply a little bit gravitational force there. All of them are small perturbation. And for this kind of situation, the small perturbation will totally change the trajectory. It's not like this. For the two-body problem, okay, if, for example, without perturbation, the original trajectory is something like that, the orbit, okay. If you add some small perturbation, like start from here, the orbit will be changed a little bit, but will keep all the main feature of the original orbit, like this. Okay. If you even increase the perturbation, it will change it to another orbit like that. So we see that it's stable, okay, with respect to the perturbation. So it wouldn't totally change. But now, okay, for this one, if you add some perturbation to this point, so initially it will only change a little bit, but soon it becomes a totally different trajectory. Okay, and because you cannot kill all the perturbation, in the reality you always have some small perturbation, all kinds of you can think about. Even when you do the experiment, even your existence of the experimental list will produce some perturbation to the system, right? Because you have mass, you may have some small gravitational attraction to the system, or you can blow some wind to the system. Even if they are small, but for this kind of system, three-body, it can change the system totally. So this is actually called the chaos, okay, or unpredictability. Okay, unpredictability. So that's the chaos. But from here, the description here, you may think that chaos is just some mess here. Okay, but in fact, it's not. Chaos, or we call the nonlinear effect, are very important in our world. Okay. Here it looks that they are quite irregular and disorder stuff, but the order, some kind of order, are actually comes from the chaos. Okay. That's a long story. We cannot explore details. But here, chaos is closely related to the self-similarity and fractal. I think we talked about this before. But so it says that if we follow some chaotic motion, we use a computer to generalize this graph. Okay. Please note that when we try to generate this graph, we have nothing. We didn't think about to generate any like a leaf type graph. We just try to use some mathematical chaotic system. Okay, it has some rule to generate some chaotic system. Finally, people got this. And of course, in the nature we have the same kind of shape. So the nature actually generated these shapes, these leaf shapes in the same way, the chaotic. Okay. And when I was a college student, we took one of our teachers to talk about the life. Okay, it says that life, what is the essence of the life from physics point of view? For physicists, life is something between the order and disorder. For a completely ordered world, you wouldn't have life. You will only have crystal, those minerals. They are perfect order stuff. Okay, in the crystal lattice. And if you have a completely disordered world, you wouldn't have the life. Okay, you are going to just have some random world. And life is something between the order and disorder. Okay, between the order and disorder. So that's the essence of the life. Okay. In fact, the discovery of the double helix, okay, the gene, how the gene is encoded, is inspired by one of the physicists. Okay, I think it's Schrödinger. He wrote a book called something like that. The mechanics view of the living organism. Okay, so something like that. Many years ago, and he inspired Watson and his colleague to invest, to try to find the structure of the life. So they are the three-body problem. So what I'd like to emphasize is that the real world is very complicated. We're only going to deal with very simple stuff like the motion along an incline and just free falling. These things, they are very simple. Okay, but the real world is complicated. Sometimes it's much more complicated than we would imagine, right? The three-body problem initially make people very surprised. They are surprised by three-body problem because we know that we can solve two-body problem, and we tend to think about, okay, three-body problem, you just add one more object. How complicated it would be. But it turns out that you cannot even solve it, even in a theoretical situation, you cannot solve it. And that inspired a lot of modern math. People developed a whole bunch of modern math to deal with the three-body problem, like Hungarian map, okay, Lorentz tracker, these things. So And another thing related to it, I think I will mention is that our weather system is actually a chaotic system. So it's sensitive to the small perturbation. So that's why we cannot predict the weather after 1 week. Okay, we can probably rely on the weather forecasting for 1 week, but nothing more than that.